theories and have a look at the equations. So we studied this equation in last week, and we know for kinetic equation of motion, there should be two components. One is a translational component, and another one is a rotational component. Okay. For translational component, we know if we use x, y coordinate system, then for translational component, we have x and y, two components. But for rotational component, this calculation can be about the mass center point G, but can be about any other points if that point can give you convenience. In last week, we used these equations for translation problem. For translation problem, one specific case is if you select point G for your calculation, you will see this item, the summation of the moment about this mass center should be 0. Why? Because alpha in translation for alpha is always 0. Okay? So we studied this in last week. And also we mentioned for some problems, for example, for curvilinear translation problem, it may be convenient to use normal tangent coordinate system like this. Okay. Now, we will have a look how to use kinetic equation of motion to solve a problem of a rotation about a fixed axis. Based on our study in week 1, we know for rotation about a fixed axis, for example, for this rigid body undergoing rotation about a fixed axis of 0.0, okay, the mass center point G is here. For mass center point G, if the rotation center is 0.0, then you can easily determine the acceleration at this mass center point G, or the acceleration at any points in this rigid body. Okay? So for example, for AG, it has two components. One is tangential component, and this is tangent to the circular moving path of this point G. And another component is normal component. Okay? And we also studied this how to calculate the magnitude of the tangent component and normal component. For normal component, it should be omega square. Omega is the angular velocity, omega square times the distance from G to O. For tangential component, the magnitude is angular velocity alpha times the distance from G to O. Okay? Now, if we know these two components, and if we use normal tangent coordinate system for a problem, then you will see for these three equations, for the first two, we can easily express the summation along normal direction and the summation along t direction, tangential direction, because we already know how to calculate AGN and AGT. Okay? For the third equation, for this one, rotational component, it can be about point G. But for a rotation problem, you can find, in many cases, to select the rotation center point O for your calculation may be more convenient. Okay? So if we select a point O for our calculation, and then we will have two items. One is IG alpha, and another one is from the kinetic moment kinetic moment for AG, how to calculate? You can see AG has two components, AGN. For AGN about point O, the moment arm is 0. Okay? But for AGT, for this component, the moment arm is RG. So in this expression here, you have two items. One is IG alpha, and another one is RG MAGT. We can rearrange this equation, and we can use parallel axis theory, and finally, you will see the summation of moment about point O, the rotation center, should be equal to IO alpha. IO is the MFI of this rigid body about the rotation center point O. Okay, so that's the equations we can use for solving a problem of rotation about a fixed axis. That's parallel axis theorem. I put this slide here just in case you have already forgotten it. Okay.